In this video, we're going to start section 5.1.2 on double Riemann sums. So whereas integrals of a function of a single variable are defined on an interval, the double integral of a function of two variables is defined over a rectangle. So a rectangle, the notation for a rectangle, often we call it R for rectangle. I know, we're creative. AB crossed with CD. So it looks like an interval and another interval that are being, what is this? This is called a Cartesian product. So it looks like the cross product, but that's not what it means. So it's the Cartesian product, and this rectangle is defined as the set of all points AB in R2. I shouldn't call them AB, should I? Points xy in R2 such that A is less than or equal to x is less than or equal to b. In other words, AB is an x interval, and C is less than or equal to y is less than or equal to d. So CD is a y interval. Graphically then, a rectangle, well, you know what it looks like graphically, but in R2, what we're talking about is a rectangle whose boundaries on the x-axis are A and B, and in the y are C and D. So all the points that are on that boundary and in the interior of this rectangle, that is our rectangle R. So a double Riemann sum, definition 5.1.1. A double Riemann sum for a function f of xy over a rectangle R, which is AB cross CD, using n subdivisions in x and m subdivisions in y, is Rnm. And it is the sum from I equals 1 to n of the sum from j equals 1 to m of f of x ij star, y ij star, delta x, delta y. So in the last video, we reviewed single Riemann sums for a function of a single variable, and you can see the similarity here. So we're going to explain these symbols a little bit more down below, but let's give a couple more vocabulary where it's here. Xij star and Yij star is called a sample point, just like in the single variable case. And it is chosen within the ijth subrectangle. I'll draw this for you in just a moment. So if the function value f of xij star, yij star, if that's interpreted as height, well, this time it's height that's over or under a rectangle. Then what we're going to see down here is when you multiply by delta x, delta y, this whole product may be interpreted as the signed volume. Signed, why? Because f can be either positive or negative, right? So it might be a positive volume if it's above the xy plane, or a negative volume if it's below. Of A, well, what is this? This is a rectangular prism. So not a rectangle like in the function of a single variable, but a rectangular prism as we go up one dimension. Then Rnm here, which is the double sum of all of these rectangular prism volumes, can be interpreted as the approximation for the net signed volume under the graph of the surface of f over that rectangular region. Let's make a sketch to make that make even more sense. So what we're saying here is, imagine that we have our rectangle. So for example, a rectangle here. And to match the diagram here, it looks like the rectangle has been divided into 1, 2 pieces in x and 1, 2, 3 pieces in y. So let's do 2 subdivisions in x and 3 subdivisions in y. So each of these things is a sub-rectangle. So I have 1, 2 subrectangles in x and 1, 2, 3 subrectangles in y. So when I say the ijth subrectangle, I mean, for example, like the 2, 3 subrectangle is the second, third, right? Second and third, that would be the 2, 3 subrectangle there. So what we do is we take a sample point in each one of these subrectangles, right? The sample point is taken within each one of these. So let's imagine that in the 1, 1 subrectangle, I take a sample point that's there maybe. So that's x 1, 1 star and y 1, 1 star. And then what do? I plug that sample point into my function. And if I'm interpreting that function value as height, well then that point gets evaluated right there. And I take the function value as constant. So what we have is a base that measures delta x and delta y. So on the graph here, delta y is here. Delta x is there. And the height, well, the height that I've taken here is f of x, in this case, 1, 1 star, y, 1, 1 star. So that length times width times height gives us volume. So that f of xij star yij star times delta x delta y is the volume of a single rectangular prism. Now, of course, I don't do this for just one of the prisms. I take sample points everywhere. So if I took a sample point there, oh, I'm backwards. I'm totally backwards. The green dot should be, if I rotate this around, the green dot should be over here. Whoops, should be over there. And the red dot will be here. But no matter, the rest of the argument is the same, right? And so if I take, let's say, the blue dot would be right in the middle, and the orange point, let's say, is here, and so that would be evaluated there, and so on and so forth, and we get heights of these prisms over the different rectangles, and when we add them up, over all of the subrectangles, then we're getting volumes. And the idea is that this represents an approximation for a function surface. A function surface that might look something like this, where you're evaluating each of these points on the function surface and making a rectangular prism underneath as an approximation. In the next video, we'll do an example with an actual function and an actual rectangle, and we will estimate the volume under the graph using a Riemann sum.